All right. Good morning, everybody, and thanks for coming in to the last GS seminar ever, as Steven said. And today we're actually delighted to have Chris from University of Michigan, who's going to talk about the exciting topic, hyperbolic equations and double null foliation of space-time. It's a nice ending to the GS seminar with a nice topic. So, Chris, please take it away.
Yeah, thanks so much, Christopher. Thanks for the invitation. It's good to be back, and I'm glad I can be the final seminar speaker while Pushkar's here. Okay, so yeah, I'm going to talk about hyperbolic equations and double null foliations, or double null gauges, if you prefer. So I'll just start with a brief overview, and the first two topics are kind of background, GR and double null foliation overview, and then the second two topics are kind of the main research points for today. Okay, so just some conventions. My spacetimes are going to be four-dimensional. They're going to have signature minus, plus, 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 and tangent vectors v, right? You have time-like, null, or space-like. And then your hypersurfaces can be classified according to, if they're space-like or null. Okay, and I want to focus on, right, this is about double null foliation. So the important ones are the blue ones, the null hypersurfaces. And these are important because they are the hypersurfaces along which massless radiation travels. So electromagnetic or gravitational waves, null dust, Vlasov fields, all sorts of things like this are why we care about null foliation. Null hypersurfaces. Okay, and an obligatory slide with Einstein's equations. Right, we have the Einstein tensor equals the matter stress energy tensor. And in particular, if we set the matter content to 0, we get the vacuum Einstein equation, so Ricci flat spacetimes. And I want to focus on, these are going to be kind of the most important equations, are going to be the Bianchi equations for the curvature. And so here I'm using W to represent the Weyl tensor of the spacetime, so the traceless part of the Riemann tensor. And this brackets notation, as usual, denotes the cyclic sum. Right, so this is an identity that is just always satisfied by the Weyl tensor of a vacuum spacetime. Okay, and just the last remark before double null foliations. These are like super important. I think when I was starting, I was always surprised how much the Bianchi equations, more so than the Einstein equations, were really, really important kind of in deriving estimates and integrating along hypersurfaces, things like this. Okay, so what's a double null foliation? It's given by a choice of two so-called optical functions. All that means is that they have gradients, which are null vectors. And I'm going to require that their level sets foliate the spacetime in a certain way. Their level sets I'm going to denote Cu and C bar, U bar. And I'm going to require that they're null hypersurfaces, that their intersections are space-like two spheres, and therefore that the space-time decomposes with a very simple diffeomorphism structure. And so just a picture here, right, I have the blue kind of outgoing level sets of the function u, and the red incoming level sets of the function u bar. And any point in the space-time, if you want to know where you are, all you have to do is ask what u value are you at, what u bar value are you at, and then what point on the resulting S2 are you at? Right, and this is going to give me a foliation of my spacetime. Null foliation because these are null hypersurfaces, double because there are two of them. This is kind of a very different type of foliation than maybe the usual TX foliation. Okay, let me also just pause for questions about notation or anything. Okay. Just some more notation. I'm going to let gamma be the restriction of the ambient space-time metric to the spheres. So this is going to be Riemannian because I required by assumption that the intersections SU, U bar were space-like. So that means that the restriction of the metric is Riemannian. And I'm going to let nabla denote the Levi-Civita connection of the ambient space-time. And anything with a slash will denote kind of the corresponding thing, but restricted to the spheres. So nabla slash is the Levi-Civita connection of the spheres. Okay, and so this is a very powerful tool. Why do we care? Well, it's used in all sorts of problems in mathematical relativity, and not all from one not all in one flavor. For instance, you have kind of these two almost opposites, like stability of various spacetimes, and then singularity formation is kind of at a different end of the spectrum. And the double null relations feature prominently in the literature for both of these applications. This is like an incredibly, this list is way too short. It's used all over the place. And it's one of the reasons that it's so important is that it's well suited, like I said, because of how null hypersurfaces are adapted to massless radiation. It's just a very well suited foliation if you're trying to analyze any type of massless radiation. So gravitational, electromagnetic, null dust, or Vlasov field, because these are going to travel along the null hypersurfaces, right? If you imagine maybe some central source that's emitting radiation, then the radiation is going to travel along the outgoing blue hypersurfaces. Conversely, in, for instance, a trapped surface formation result, if you have incoming radiation that you're trying to focus in the future and form a trapped surface, that's going to be traveling inwards along these red incoming hypersurfaces. Okay, so just a slide kind of motivating why we would care to study these double null foliations. Oh yes, and kind of another crucial point is that they're the natural setting to consider the characteristic initial value problem, which instead of prescribing initial data at time t equals 0, you prescribe it along the initial hypersurfaces, so C0 union C bar 0. Okay, now that I've defined my double null foliation, let me introduce some notation for various vector fields that we're going to decompose things with respect to. So E3 and E4 are going to be the tangent vectors of the outgoing and incoming null hypersurfaces. So these are going to be null vector fields, and then I'm going to let EA, so E1 and E2, be kind of the remaining degrees of freedom, so tangent to the SUU bar sections. And just so a picture here. So I have my E4, these are kind of the outgoing vector fields. E3 is the incoming vector fields. And then, capital Latin indices will always be 1 or 2. So those are kind of the frame fields for the remaining S2s in the spacetime. Okay, and once we have a frame like this, E1 through E4, what do? We like to decompose things, and we can decompose the Weil tensor of a spacetime. Once we fix this double null foliation and fixed our null basis here, we can decompose it into various S-tangent components. So for instance, if I plug in E4 here to the Weil tensor in these two slots, and leave the other two slots kind of open for unknowns, I get a 2 tensor, and I'll call that alpha. And I have alpha bar, where instead of E4, I've slotted in E3 here. And so these are related by what's called conjugation, which is just wherever you saw an outgoing kind of E4 object, instead replace that with an incoming E3 object. So you have beta, where you're plugging in some different combinations of the vector fields, beta bar, where you're kind of flipping it, and instead of doing it for the outgoing direction, do it for the incoming direction. And then you have the remaining scalar things. And so, the exact formulas here are not important. What's important is that we're just decomposing the Weil tensor into kind of more manageable pieces that are adapted to this double null foliation. Sorry?
What are the E1 and E4?
Yes, E1, E4 are these vector fields here in the top. So the E3 and E4 are the main ones. Those are the tangent vectors to the null hypersurfaces. And you should think of those as E4, for instance, is like the velocity vector, the forward velocity of like outgoing radiation.
I see.
And E3 is the incoming velocity of radiation.
And the EA?
EA is just the remaining, right? It's a 4-dimensional spacetime. E3 and E4 is only 2 dimensions. So EA is kind of the remaining space-like frame. Yeah. For like a frame field tangent to the surface of the Earth would be the EA. Yeah, and then so on this notation, on this slide, I kind of at the bottom here, I mentioned that slashes denote things restricted to the spheres. And if you look at this nabla/3 here, that like a priori might be a little strange because E3 is not tangent to the sphere. So like, what does this mean? This is just going to be notation for I take the ordinary derivative of a tensor field C in the E3 direction, and then I project the result to the spheres. But basically, we want everything to be kind of intrinsic to the spheres. And so we're just projecting this derivative. This notation will come in later. Okay, yeah, and please interrupt me if you have questions. Okay, so given a Weil tensor W, we have its null components here. And I just want to remark that the ones at the top, alpha and alpha bar, are symmetric and traceless tensors. This just comes from the fact that, so the symmetricness of alpha and alpha bar comes from the pair interchange symmetry of the Weil tensor, and the traceless part, the fact that alpha and alpha bar are traceless, come from the fact that the Weil tensor is a traceless tensor. And when I say traceless in this gray box here, I mean with respect to the gamma, the metrics of the spheres, not the full spacetime metric. Okay, so we have decomposed the Weil tensor, and I have already written the Bianchi equations for the Weil tensor there. So now we want to decompose the, see what the Bianchi equations imply for these null components that I've just written out here. And before I list them, I just want to just kind of real quick as further motivation, why am I doing this? This is just to kind of a crash course on like deriving the Bianchi equations in a null frame, which for instance, Christodoulou and Kleinerman do in Minkowski stability and is, done earlier, but I'm just kind of briefly going through it. Instead of just presenting kind of the full list of 10 null Bianchi equations. Okay, so in schematic form, which I think is really useful, and in particular is pretty useful for kind of the second half of this talk, to think of them like this. The Bianchi equations take the form of two sets of propagation equations in the E3. So the first one is in an E3 direction, and the second one is in the outgoing E4 direction. And I'm just using this psi, right? This is just a schematic kind of heuristic. So psi is just going to denote an arbitrary one of these Weil tensor components, and gamma is going to denote an arbitrary Ricci coefficient of the spacetime in this double null foliation, right? So the gamma are just the Christoffel symbols of the frame E mu. And right, so this last paragraph is important. So these are propagation or transport equations for Weil tensor components. And so we can use them to obtain LP estimates on the Weil tensor components psi. Right, so if you look at Minkowski stability or trapped surface formation, this is kind of these are the crucial equations where you get estimates on your curvature components that allow you to close various bootstrap arguments you do by integrating these null Bianchi equations. Any questions about that? Okay. So before I write them in a bit more detail, just some motivation for, again, why we're studying, which I've already alluded to, right? They're in Minkowski stability and trapped surface formation. But basically, these equations that you get, these null Bianchi equations and kind of corresponding equations for the Ricci coefficients or Christoffel symbols, have really good structure. You get these propagation equations that I've just shown you, but you also get elliptic equations on the spheres, div curl systems, things that have really nice mathematical structure. And furthermore, even in works, earlier I presented kind of a incomplete list of citations for works that use double null foliations, but even in works where they don't explicitly use a double null foliation, the null Bianchi equations are widely used. So for instance, in the original Minkowski stability proof, they don't use a double null foliation, they use kind of a mixed TU foliation. But the null Bianchi equations are crucial to their argument. And this is true in Zitzer's proof of stability for Einstein-Maxwell, and in Lydia Beery's proof generalizing the original Minkowski stability result. So that's kind of, there's even more motivation to study null Bianchi than there was to study the double null foliations. Okay, and so what are the null Bianchi equations in a slightly more, slightly less schematic, slightly more rigorous form? So for the components alpha and beta, right, I'm dropping the W in brackets from the notation just so I don't have to keep writing it, but these alpha and betas are the components of the Weyl tensor itself. And then you have some more equation, and basically I'm writing them in pairs here because the fact that these are coming in pairs, so this first pair here, the conceptualizing this as pairing alpha, the nabla3 alpha and nabla4 beta, thinking of these as paired kind of is where the Bianchi equations get their hyperbolic structure in a double null foliation. And some notation here, right, you'll notice that all of these are transport equations, so either in the E3 or the E4 directions. And on the right-hand side, you have various first-order differential operators that are spherical, that are restricted to the spheres, right? So nabla slash is just the derivative operator of the spheres. Div and curl with a slash are the divergence and curl operator of the spheres. This thing that appears in the first equation, nabla3 alpha, on the right-hand side, is just going to be the symmetrized covariant derivative of beta, but it's traceless part. And star will denote a Hodge dual with respect to the spheres. But really, you know, the details here aren't crucial. What's crucial is that you have propagation equations, so a null derivative in the E3 or E4 directions on the left-hand side, and then kind of spherical first-order differential operators on the right-hand side. Okay, and so the key point is the fact that Einstein's equations are, you know, said to be hyperbolic. How is that reflected in this system of equations? And it's and this is where I'll talk about that. So the key point is this idea of Bianchi pairing, which is that the principal part of the equations on the right is up to a minus sign the adjoint of the principal part of the equations on the left. So for instance, in the top row, the divergence operator on two tensors is minus the adjoint of this nabla slash hat O times of this kind of symmetrized traceless covariant derivative operator. And I've just rewritten it here, and this is really kind of the punchline is it's just saying that we can integrate by parts, right? If we have a divergence on an alpha, we can throw that derivative to the other function with a minus sign. And so this L2 adjoint property gives the null Bianchi equations their hyperbolicity. We'll see what I mean by that in a second. I'm citing Taylor here, Martin Taylor, because his Vlasov stability proof gives kind of a really nice description of this. I should mention that, you know, this is used much earlier in the 90s, for instance. The idea that these equations, the right-hand sides are not just random first-order operators, they have a very precise structure. Okay, so this is kind of the end of the kind of crash course on GR double null foliations and null Bianchi equations. So I'll pause for a drink and see if people have questions. Okay, so kind of what I want to go, where I want to go from here is I want to study this structure in more detail. So this Bianchi pairing, and so I'm going to introduce the idea of a double null hyperbolic system as like this, and it should be reminiscent of the kind of schematic form of the null Bianchi equations, where you have some transport equations in either the E3 incoming or the E4 outgoing direction. And on the right-hand side, you have some first-order spherical differential operators. And so, yeah, let me explain what I mean by this a little bit more. So I have some integer big N, and I'm going to consider 2n unknown tensor fields that I'm going to denote by psi I and psi bar I. And each of the psi i's with no underline are going to be required to satisfy some incoming transport equation. That's that top line there. And the psi bars are going to be required to satisfy an outgoing nabla4 transport equation. And the crucial part here is this first bullet point here, where the principal parts of the right-hand side that I've denoted d slash with psi or psi bars. These are going to be first-order differential operators on the spheres, which are anti-adjoint in L2. So just like requiring that this integration by parts thing here can be done again, right? How divergence and this differential operator here were minus L2 adjoints. I'm going to require that when I write it like this, these principal parts on the right-hand side are L2 anti-adjoint. These E's are just lower order terms. I'm going to require to be of the form Christoffel symbol times unknown, which is exactly what they are in the Bianchi equations for the spacetime. And again, just like before, this first point ensures that we can integrate by parts on each SU bar, on each sphere. Right, I can throw this deep psi over to the other function. It changes to a minus deep psi bar. Okay, and right, these are transport equations in certain directions, so it's very natural to consider them to be in the characteristic initial value problem where you're prescribing initial data not along a space-like t equals 0 slice, but along these initial null hypersurfaces. And again, I've just drawn these vector fields to visualize kind of which directions are these transport equations propagating in. Right, the idea being that if we just focus on the first set of equations, these Nabla-3 equations first, then I would think of initial data, psi naught, being prescribed along these outgoing C0s, these blue cones. And then I ask, how do they evolve in time? Well, the equation tells me how they evolve in the red E3 directions. And kind of conversely with the psi bars, those are prescribed on the C bars, these initial C bars 0. And then the equations tell me how that unknown propagates, how it changes in the outgoing E4 direction. Just to have an example to ground this, I'll explain the color coding in a second, but these are just the two Bianchi equations written out in slightly more detail than before for alpha and beta. So here my big N is 1, and my collection of unknowns are just psi 1 being alpha, psi bar 1, I'm going to denote beta. And in these equations I've color coded, the unknowns are red, the Christoffel symbol geometry part is blue, and the leftover rho of W and sigma of W, those are not unknowns, those are the actual components of the Weil tensor of the underlying spacetime. And I'm imagining kind of replacing in the Bianchi equations the Weil tensor components, alpha and beta of W, by just general unknowns that I'm thinking of trying to solve for. Right, and other natural examples are just various other subsets of null Bianchi equations, as long as you pick the right ones so that you have this Bianchi pairing. Let's see if I can go back real quick to, this list of null Bianchi equations. Right, if I kind of pick the second line of Nabla-3 beta and Nabla-4 of rho and sigma, that would be another kind of double null hyperbolic system. So with this example, what can I say about these systems? Well, kind of the crucial property that I've been talking about, this Bianchi pairing, or this anti-adjoint property that lets me integrate by parts. Why is this important? Well, just because it allows us to kind of get a controlled quantity. And anytime you get a controlled or conserved quantity in PDE, you're very happy. So if I define the energy to just be of some unknown psi, to be the L2 norm, I guess 1/2 the square of the L2 norm on the spheres, I can get some kind of conserved quantity. So I'm just computing heuristically here, where I have, I'm trying to, show that maybe this energy is conserved. Of course, I won't get that exactly, but I can instead get something nice instead. So let me take the Nabla-3 of this energy, right? It comes inside the integral. And by the equation, I know that this Nabla-3 of psi is equal to d slash of psi bar, right? This is just using this first equation here. Once I have this, I use the L2 adjoint property to integrate by parts and put this differential operator on the other function. And now I use the fact that that was the principal part of a nabla 4 psi bar equation. And then I can pull that out of the integral, and that just is equal to lower order terms plus or minus rather the nabla 4 derivative of the energy of kind of the conjugate psi bar. And so what I get is once I integrate this, sorry, this is not once I integrate this, I'm about to integrate this. It's this differential kind of equation here where I have two different null derivatives. And I'm going to integrate this over the full space-time. And what I get is, so not in a control of this initial energy, like math calligraphic E, but rather integrated along the null cones, right? So you remember E was an L2 norm on the spheres, but on this block, in this colorful box here, these are L2 norms on the cones. So I am kind of losing a little bit. I have to be integrating on the cones, these null hypersurfaces, CU and C bar U bar. But what I can get is that any of these integrals on the cones is controlled by its initial data. And this is, the crucial part of why we care about this Bianchi pairing in the first place. Again, this is, heavily used in Minkowski stability and probably earlier than this. This is the kind of gold standard for how you derive estimates on the curvature components in a spacetime. But remember here, these psi and psi bars can kind of be arbitrary unknowns that satisfy a double null hyperbolic system, a DNH. And so the first thing you want to show for this type of system is a well-postedness result. So here is kind of a low regularity well-postedness result. If I have some background spacetime mg, and I have some initial data that lies in certain Sobolev spaces, I'm happy to talk more about the details here, but essentially this psi 0 and psi bar 0, all I'm requiring is that they have one derivative in L2 in the spherically tangent directions. And then I'm just requiring continuity in the other directions, kind of in the null directions. And then given this, I can show there exists a unique weak solution where weak solution is interpreted in the sense of integration by parts with a test function. And then I have the second bullet point here. So they're actually continuous in a certain space. And that continuity lets us say that there's enough regularity to make sense of an initial value problem. So basically, this is kind of a local existence and uniqueness result for the characteristic initial value problem for systems of this type at low regularity. Okay, so right, so this is kind of the first result one would want for these systems, but we want to kind of ground these in things that are interesting in GR, and remember these came from studying the Bianchi equations. So now what I want to do, maybe I'll pause if there are any questions about this theorem. This is kind of the first of two main kind of research points I want to make here. Yeah, so after this, what do we want to do? Well, what I want to do is I want to fix a vacuum spacetime in the background, and I want to study the Bianchi equations on this vacuum, on this background spacetime. And so how I'm going to do that is I've been writing the null Bianchi equations before, which were these equations for the Weil tensor components alpha w and so on. And I want to, as I did in this example right here, I replaced some of those Weil tensor components with unknowns. I want to do that for all of the equations. And I want to replace, in the Bianchi equations, anytime a Weil tensor component appears, I want to replace that with an unknown. And so this is my system of linearized Bianchi equations. This gamma dot psi on the right-hand side is kind of just a loose notation for the general lower order terms. And because earlier I actually, in the genuine Bianchi equations, I didn't have a brackets W just kind of because I didn't want to keep typing it out. Here, this is really substantially different. I'm saying that these alpha, beta, rho, sigma, and so on, these are not the space-time Weil tensor components. These are just unknowns, and I'm trying to solve this system to solve for these unknowns.
So gamma is gamma.
Gamma is fixed
No.
because that's of the background spacetime. Yes, you have to have a fixed spacetime and a double null foliation. Yeah. Right. So, like I was saying, right, these alpha and betas and so on, these are unknowns. These are not components of the spacetime's curvature tensor. And I'm assuming vacuum now, so I could replace the word vial with Riemann. And gamma denotes the Ricci coefficients of the spacetime, which, as Puskar pointed out, these are known quantities. And this psi, kind of as it did before, denotes an arbitrary unknown. And the word linearized here refers to the fact that the coefficients in these equations, these gamma, no longer depend on the unknowns, right? They just depend on the background spacetime, which is fixed. I would stress this point because the genuine Bianchi equations, these are already linear in the curvature components. So I just want to say, why am I calling these a linearized Bianchi equation? And it's just the fact that I'm decoupling the unknowns from the geometry of the foliation. Okay, and I would want to apply this theorem. Why would I kind of give a talk with both of these kind of very related concepts of what I would want to apply the past theorem that I just presented on? But the problem is that many of the unknowns satisfy two independent equations, and so the system is overdetermined. Right, if I just go back here, right, on the top right, I have a nabla4 equation for beta, but then the first entry on the next line is a nabla3 equation for beta. So kind of which one do I choose? And so one possible fix that I kind of explored in the paper this talk is based on is you choose some subset of the equations to be constraints and the rest to be your evolution equations. And then you hope that under the flow of the system, the evolution equations that you've picked, you hope that the constraint equations propagate if the initial data satisfy them. And that's kind of more on this later. That'll be kind of a main talk of if do these constraints propagate or not. But before we even get to that, we need to say, well, how do we choose which of these 10 equations, 8 equations are constraints and which are evolution equations? And one answer that I chose, but this is by no means like a unique prescription, as you will see. So I'm interested in if there are other more natural ones. But you choose to be so that your resulting system is as hyperbolic as possible, because at the end of the day, you would like to apply this theorem that I earlier quoted on well-posedness for these double null hyperbolic systems. And we do have a little bit of a starting guiding light, which is that alpha and alpha bar, these unknowns have only one equation each. So to be well posed as an initial value problem, these must be viewed as evolution equations. But unfortunately, there's no way to choose from this full set of linearized Bianchi equations in such a way that this full system is hyperbolic, but also the system is not overdetermined. So, that's kind of one shortcoming of this method of choosing constraints and evolutions. So let's go through just to get a little bit more concrete. Let's choose our constraints and choose our evolution equations. So I've written here the full set of linearized Bianchi equations, and now we're going to choose evolutions and constraints. And I've already boxed in the alpha equations and alpha bar equation because those are the only equations that these unknowns have. So I need to include them in my list of evolution equations. Okay, and my prescription, remember, is I'm going to try to choose evolution equations such that the resulting system is as hyperbolic as possible at every step. So if I just look at this first equation for alpha, its Bianchi pair, the equation that we need to integrate by parts, is the nabla4 beta equation. So I'm going to go ahead and add that to my list of evolution equations. Okay, but now I already have an evolution equation for beta, so this equation, nabla3 of beta, I can't include that or else it would be an overdetermined system, so I'm going to throw that into my bucket of constraint equations. Okay, I think, yeah, this slide I feel like is out of order, so let me go to this slide and let me focus on the fact that, well, I just put nabla3 beta in my constraints bucket, and its Bianchi pair is this equation, so I'll also throw that rho sigma nabla4 in the constraints. And if this is a constraint, well, I need some evolution equation for rho and sigma, so I'll put that equation in the evolution equations bucket. And then I want, to be as hyperbolic as possible. I need to throw in the Bianchi pair, which is this nabla4 beta bar equation. And now you see that kind of this warning that I had on the last slide with bullet points that you're destined to fail at some point, which is that this remaining unboxed equation is the Bianchi pair for nabla4 alpha bar, but I already have an evolution equation for beta bar. So I'm forced to put that last one in the constraint equations. And, as a result, this set of evolution equations is not hyperbolic. This nabla4 beta bar doesn't have a Bianchi pair. So what do we get here? Just kind of recapping this whole process a little bit more clearly. I have a set of evolution equations and a set of constraint equations. And I'm just giving these kind of left-hand sides a name so that I can talk about them later. Right, and kind of a key thing here, kind of a tautology really, but important, is if I now, instead of if I denote psi by this whole collection, so kind of this whole collection of solutions of unknowns, a collection of tensor fields satisfies the full linearized Bianchi system if and only it satisfies both the evolutions and the constraints. Right, so the natural question is, okay, can I just prescribe initial conditions that satisfy the constraint equations and then show that they propagate, that they're preserved by the evolution equations? This is what I would like to show. And unfortunately, the answer is no. And it's not unless there are additional constraints that are satisfied by the unknowns. So just a quick recap here. Right, I'm trying to solve the Bianchi equations, by which I mean the linearized Bianchi equations. I've kind of recast them into an initial value formulation here, a characteristic initial value formulation. And I need to satisfy both the constraints, and then I need to evolve them and hope that the constraints still are satisfied. These constraints in the lower box here, I'll refer to as the differential constraints, simply because there are derivatives appearing in them. Right, and so what this is saying, what I'm claiming here, and what I'll show in the future slides, is that actually that green box of constraints can't be guaranteed to propagate unless there are some additional purely algebraic constraints that are satisfied by the unknowns. So I was kind of surprised when I found this. And to discuss this, I want to introduce some notation. So I just want to introduce the notation of like the vector bundle of the solution space to these equations. And all this is just saying that if I have a psi, so alpha, beta, rho, sigma, beta bar, alpha bar, this is just saying that alpha and alpha bar are symmetric traceless 2 tensors, beta and beta bar are 1 forms, and rho and sigma are scalars. So this calligraphic V is just this vector bundle whose fiber over any point is kind of the space where the solutions to the Bianchi equations live. And just for brevity, I'll also let this omega 1, so 1 forms, but with a subscript s, denote the set of s tangent 1 forms. These are 1 forms that are tangent everywhere to these spherical sections, SU, U bar. Okay, so this is the theorem I'm presenting that kind of answers this second bullet point here, that there have to be some additional constraints. So what does it say? Well, I fix a vacuum spacetime, my background spacetime, with a double null filiation. It turns out there's a vector bundle morphism L that maps from my solution space V. It has some, codomain given by the right-hand side. That's less important. The important part is this vector bundle morphism. So right, it just means it's a linear map at every point. It depends only on the Riemann curvature of the underlying spacetime. And any solution of the linearized Bianchi equations has to lie in its kernel. And okay, you might say if this math frac L operator is the 0 map, this is not a very interesting theorem. So kind of the second important part of this is that as long as you're not isometric to Minkowski spacetime, then the dimension of the kernel of this operator is strictly less than the dimension of the full solution space. Right, so you're saying it's kind of, there's some interesting kernel here. And kind of the corollary, the punchline here is that solutions to the linearized Bianchi equations must lie in a codimension at least one subspace of my full solution space B. And why is that interesting? Well, it's saying that, for instance, if you go back to Minkowski stability, when Christodoulou and Kleinerman were working on this in the 90s, they have this first paper on the linear field equations that they call the spin 2 field equations, which are essentially what I've written here, the linearized Bianchi equations on Minkowski spacetime. And they studied the dynamics and the asymptotic behavior of solutions to these linearized Bianchi equations. And so one might be interested in doing so on other background spacetimes. And you might be interested in studying various solutions to them. And a priori, you would be able to study solutions that lie in this calligraphic V space, this full solution space. But what this theorem says is there's actually some strict subset of codimension at least one that your solutions have to lie in. So for instance, this also has kind of implications on stability problems. If you want to study perturbations to the Bianchi equations, this theorem says that you cannot arbitrarily perturb your initial data. It has to be a perturbation that kind of lies in the subspace, which is the kernel of this operator L. It can't perturb outside of that. So that's kind of the punchline of this theorem. One example, to give some more concrete examples here, is in Schwarzschild with the standard Eddington-Finkelstein double null gauge. In this case, the curvature components are all 0 except for rho, and then rho is minus 2m over r cubed, where m is the the mass parameter and r is the radial distance. And the map L then can be very explicitly written down. So I do want to mention that this L here, in general, can be written down explicitly. It takes it takes half a slide, but it's not an abstract map. It's a very explicit computable thing. And in my paper, it's written down. In the Schwarzschild case, it's very simple, very explicit. L of my solution, or L of my alpha beta rho vector, is just some scalar factor times beta bar comma minus beta 0, 0. And so right clearly, if I am in the kernel of this, that means that beta bar and beta have to be identically 0. Right, so that means that if I want to study the linearized Bianchi equations on Schwarzschild, actually the beta and the beta bar both have to be 0. And I'm really only studying kind of dynamics for alpha, rho, sigma, and alpha bar.
Sorry, can I just interrupt and ask something here?
Yeah, thanks.
Hello. So just to ask, this L is being explicitly constructed in terms of alpha, alpha bar, beta, beta bar, rho, sigma for every space-time, in the sense that, there exists, your theorem says there exists such an L, and the L is given explicitly by this formula, or do you just prove the existence? And so, how do you obtain the fact that the map L is what it is here? That's my question. Thank you.
Yeah, no, thanks for the question. Exactly. So I think I have in a different tab here, I can find where it's written down. I will abandon the effort if it takes too long. But yeah, it's for any spacetime. The kind of asterisk there is it has to have admitted double null foliation, which any spacetime will locally. So this is not too big of a problem. Okay, let me not talk until I finish scrolling. So here we go. So this is kind of the explicit construction of this map L. And I've written LW here to know. Right, so you can see it's various kind of quadratics. Or sorry, they're linear in the unknowns, alpha, but they're always multiplied by the curvature components of the spacetime.
Of the known spacetime, yeah.
Yes, of the known spacetime, exactly. Yeah.
Thank you.
Yeah, thanks for the. Sorry.
Thank you very much.
Yeah, thanks for the question. Yeah, please let me know if there are any others. Right, and if you go to this formula, you plug in a lot of things in Schwarzschild vanish, then that's exactly how you get this slide here. Okay.
Please.
Yes.
Something to do with positive mass theorem here.
Oh boy, how's that? Okay.
like if it's not Minkowski, then you can't have arbitrary perturbations. Like
I
if you have
see.
arbitrary perturbation, that is actually trivial. It should be trivial if you just randomly perturb it. Like you have to have this sort of constraint. And there's M coming up here.
Yes, that I had not thought about this at all. That's really interesting. Yeah. I would love to talk more about that for sure. Yeah, right. It's saying that as soon as you're outside of Minkowski, you have some non-trivial restriction on your solutions to the linearized Bianchi equations. One thing I want to note here before I go, I think in the last kind of, do I end at 50 or at the hour?
You can go till like 12. Yeah.
Okay. Yeah, so I'll have time to present the proof idea. Before I do that, I want to have a remark here, which is that these constraints were kind of derived. If you go back to, sorry, this will take a bit there, to this kind of method of choosing which were constraints and evolutions. And so all that to say that kind of this, throwing things in the evolution bucket or the constraint bucket, there are different ways to do this, and presumably this would get you different operators L. And so, I haven't had time to think about what that means, what kind of the intersection of the kernels of these operators would be. But you know that it can't be, basically Minkowski gives you examples where the kernels can't intersect to be too trivial because you can have arbitrary perturbations in Minkowski. So basically, I'm just curious on kind of what other analogs of this would be if you kind of look at other prescriptions for how to make this procedure, for how to do this procedure of choosing evolutions and choosing constraints. Any last questions before I talk about the proof idea? Okay, so in the last 5-10 minutes here, so the proof idea is pretty simple conceptually, and it's just kind of a lot to write down. You're just cross-differentiating basically. So you have these 4 constraint quantities that were here. You have this lower box here, this psi, p, q, and psi bar. And in the paper that this is based on, of course, you don't just have this vague gamma dot psi. You have the explicit expression there. And I just take derivatives. So, let's look at this xi. I take a nabla 4 of that, for instance, and then I kind of commute derivatives, use the nabla 4 beta equation here, and I get various, various expressions. And for these expressions, I insert everything I know. I use the evolution equations, and I use the null structure equations for the background spacetime, and I get, a lot of terms. So I guess this is for xi bar, not for xi, but just for example, in this top line, I've written out what is nabla 4 of xi bar, of the xi bar constraint. And what you do is you just, at every point, you try to apply either so this is the top order in unknowns expansion. So let's look at this just rightmost term, this nabla 4 of trace chi bar plus omega bar, beta bar. The leading order term in that, in curvature, or sorry, in the unknowns, is when the nabla 4 hits the beta bar. And when that occurs, I use the evolution equation for beta bar to write that derivative as this nabla sigma minus nabla rho. And I do that for every term here. I get a lot of things, and then I have to, this is, there's a lot of terms, and there's especially a lot of lower order terms. And if you maybe look at, let me just go to this other tab here again, and you look at the expressions for this map, all of these are 0th order, right? There's no derivatives here. And so you can't just forget the lower order terms. So it's kind of, they are the messiest, but it's also kind of where the interesting thing for this theorem is happening. And so, okay, you get a lot of terms, and at the end of the day, so we have this differential constraint xi bar in this example. At the end of the day, you get that the derivative of a differential constraint is equal to some expression, which you can separate into two terms on the right-hand side. The first is terms that are 0 if and only if the differential constraints vanish. And the second is just a leftover bunch of terms that's going to end up being our operator L. And the linearized Bianchi equations hold if and only if, as I said earlier, both the evolution equations and the constraint equations hold. And so in particular, the left-hand side and the first term on the right-hand side vanish, and therefore the leftover terms have to be 0. Right, this is essentially just a long kind of cross-differentiation computation, and then you get some equation where all of the terms have to vanish because, all of these terms have to vanish because by assumption they satisfied certain collections of equations, and so the leftover term has to be 0, and that's just what the operator L is defined to be. Okay, and some consequences of this, right? So as I mentioned earlier, solutions to these linearized Bianchi equations are more constrained than expected. In Minkowski, for the quote-unquote spin-2 field equations in flat spacetime, you could study arbitrary solutions, arbitrary perturbations. You can't do that in arbitrary spacetime because these additional algebraic constraints must hold. And kind of a corollary of this is that in particular, you cannot arbitrarily perturb initial data for the linearized Bianchi equations. And some further questions are, well, one, is this algebraic constraint being satisfied? Is that sufficient for solving the linearized Bianchi equations, right? This theorem says that it's a necessary condition, but is it sufficient? And are these algebraic constraints, do they propagate under the evolution equations? And this last question is actually, at least from my point of view, not as easy as it sounds at first, because, for instance, when I showed you the formula for L, there were terms where both alpha and alpha bar of the underlying spacetime and the unknowns themselves, alpha and alpha bar, where they both show up in the same term. And alpha and alpha bar, they only satisfy one equation each, and they're in opposite directions. So if I have something like, alpha, maybe just some equation like alpha that involves alpha and alpha bar, and I want to show that it is 0 for all time, the first thing you would think to do is make sure it's 0 initially and take a derivative and show that it has to remain 0. But if you take an E3 derivative, only alpha has an evolution equation in E3, and alpha bar, you kind of don't know what to do. And if you take an E4 derivative, you have the same problem. So it's kind of just some interesting, I'm not really sure how to go about showing that. Another thing more physical is, what are interpretations of this operator? And then kind of the nonlinear analog and what this, implies for the full Einstein equations. The reason I thought about this is I'm interested in kind of, their local existence and characteristic initial value problem for the Einstein equations, of course, has been known for a long time now. But even in the characteristic case in Rendell's theorem from the 90s, he reduces it to a 3+1 kind of wave gauge harmonic coordinates method. And I'm curious, just because the null structure equations, null Bianchi equations are so important nowadays, I'm curious if there's a proof of local well-posedness for Einstein equations that's carried out entirely within a double null framework, where you're treating the Bianchi equations really as the main system. And so that's kind of my overriding motivation here. And yeah, I think with that, I'll say thanks for listening. And if there are any questions, I'm happy to talk about them.
Thanks, Chris. You want to talk? So anybody from the audience, if anybody has any questions, it's time to unmute yourself and ask Chris. Do you have any questions from the audience? Anybody? Yes, it's like the map is really interesting. Yeah.
Thanks. Yeah. It's just this kind of thing that where if you're trying to show that these constraints propagate, you just get these leftover terms, and so they must vanish. There's also, I want to distinguish this from like linearized gravity, for instance, in like DHRT, where they're talking about this. They're linearizing the full Einstein equations. This is kind of like a half linearization where your connection coefficients for the underlying spacetime are given, and the curvature is kind of the thing you're linearizing about. Yeah. So for instance, they study perturbations to linearized gravity, and this theorem is like not at all saying that that's not possible. It's saying that if you fix your background spacetime and just linearize the Bianchi equations, then there's this restriction.
Restrictions, yes. Like, you think it's possible, like, to get the weak solutions in the full system, like full Einstein equation with the weak solution here, you need the L2, right? The L1.
Yes. You mean the like local wall posedness part of this?
Yeah. So the regularity is the initial data is in H1, I think.
Yes.
Right?
Right. Yeah.
Yeah, H1 of the surface, and L2 of C, right?
Yes. Yeah.
I think so.
Sorry, go on. Yeah.
So if you actually include the full nonlinear equations,
Mm-hmm.
do you expect that still this regularity, because nonlinear terms kind of like the dangerous term for the weak solution, but they're like quadratic, right?
Yes.
That we that's
Yeah. So I mean, what ended up being too big for this first paper is like having also the null structure equations and putting them into the double null hyperbolic system framework. In some sense, it's easier for them because they're ODEs for the most part. They're either constraint equations or they're ordinary differential equations. There's no spherical derivatives in an evolution equation.
Yes.
So I think you could, just based on, that's my original motivation.
Yeah, because null structures, usual like nonlinear wave equation, if you have null structures, you can have weak solutions because of the cancellation.
Yes.
And that's what I'm wondering. That's actually very interesting. Yeah.
Yeah, I'm not sure about the regularity that you would need, but I imagine it with higher regularity at least. I do think it could be done.
So can I ask something else? When you say completely in double null foliation, right? For example, I'm thinking of this first paper by Jonathan Luke, right? Where essentially he extends essentially the theorem of Rendell, right?
Yes.
So, but he somehow uses it again. He somehow uses the Cauchy problem to get some initial, right?
Exactly. So
some
even
initial.
there.
Yeah.
Sorry, go on.
No, that's the thing. Like he somehow uses it already to use some space time, and then he uses the a priori estimates to sort of build an energy that is being built and built. It's a standard continuation argument, So your question here late was like how to do this in the absence of a corresponding theorem by Rendell here, because also the regularity is in question now, right?
Yes.
I see.
Yeah, because Luke, even the start of his argument is a Rendell type wave gauge thing, and then, like you say, he uses the null Bianchi equations for the a priori estimates to close the bootstrap continuity argument. So I'm kind of interested in how do you start that off just using the Bianchi equations.
Oh, that's very nice. I see.
Forget about Cauchy slides, Cauchy problems.
Right, exactly. It seems kind of very natural to ask, can you do this entirely within these null hypersurfaces?
One could have proven historically first this before moving to the Cauchy problem, right?
Right,
that's
exactly.
Thank you. Yeah, awesome.
Yeah, thanks so much.
Interesting.
Oh yeah, that's the name of the compensatory compactness. If you have null structure, then you have this compensatory compactness. That's the name, I forgot it.
Oh, really? I've heard these words. I don't know too much about them.
They're from Slack, actually.
Oh, yeah. And like Koenig, right? Does Koenig deal with this? Carlos Koenig?
Yeah.
Compensated compactness is also used very heavily in conservation laws in divergence form
Oh, okay.
complementarily. Yeah,
Interesting. Yeah.
yeah, L infinity solution. Anyway.
Do anybody have any more questions? Because
No, Pushkar.
all right, so we're gonna start the recording.